VLSI data conversion circuits, lecture 45. In the last class we were looking at the preamp, and I wish to make one last minor point about it. This is the single ended equivalent of the preamplifier with the auto zero capacitor in place. During the auto zero phase, these switches marked in green are closed, but during the amplify phase the equivalent circuit looks like this, with the appropriate value of estimated offset stored on CAZ. As we saw the last time around, the input of the preamplifier itself has some parasitic capacitance Cp, and we saw that it makes sense to choose CAZ to be not so small as to cause a big attenuation due to the series combination of Cp and CAZ. On the other hand, you do not want it to be very large either, simply because making this capacitor CAZ get charged to the estimated offset value becomes difficult, because the preamplifier has to drive this load capacitance, and depending on the nature of the preamplifier the trade offs vary, but one thing can be said, that if you want to charge a larger capacitor to the same voltage in the same time, it means that a larger amount of charge must be deposited on this capacitor, which in turn means that current somewhere must be larger. Okay. So, it is appropriate to choose Cp not to be so large as to make it difficult to charge, nor so small so as to make this input signal smaller across Cp because of this finite attenuation. The last point that also precludes making CAZ very large is that in practice it so turns out that CAZ is accompanied by a bottom plate parasitic capacitance. So, one of the plates of CAZ, if not both, have a capacitance from the bottom plate to ground. So, this capacitance is, let us say, about this capacitance is about 10% of CAZ, which means that clearly there are two ways of physically placing this capacitor. One could either place the bottom plate towards the input as shown here, or take the opposite stand and place the bottom plate here. So, the question is, which of these two strategies makes sense? Clearly the attenuation from V in to the voltage across Cp in the first case becomes Cp by, or rather I am sorry, CAZ over CAZ plus Cp. In the second case it is CAZ divided by CAZ plus 0.1 CAZ plus Cp. Clearly this capacitance is larger, therefore it means that there is less attenuation here when compared to the case where you put the bottom plate to the right. Can you comment on the input capacitance looking in both cases? Please recall that in a good design CAZ will be much larger than Cp, because you want to make sure that the attenuation due to the series combination of these capacitors is small, which means that virtually all of Vn is appearing across Cp, which means that the input current is simply the current being drawn through the parasitic capacitance plus the current which is being drawn through this 0.1 CAZ. So the Cin in this case is approximately the bottom plate capacitance, which is 0.1 CAZ as an example, plus Cp. How about here now in the second case? Again, if you assume that CAZ is large, which is what you would do in order to make the voltage at the input of the preamp roughly the same as the main input, you will find that the input capacitance is approximately 0.1 CAZ plus Cp, and this means that regardless of the orientation of this capacitor, the input capacitance is the same, which means that the sample and hold has to drive the same amount of load capacitance whichever way you choose the orientation of the auto zero capacitor. On the other hand, the first choice, namely putting the bottom plate on the sample and hold end, prevents unnecessary attenuation of the sample and held voltage by this series combination of Cp and CAZ. So this is the preferred approach. In other words, you want to put the bottom plate parasitic towards the left side or the sample and hold side. Is this clear? All right. The next thing is to try and figure out how one might be able to design using transistors a preamplifier where the basic idea is to take a differential voltage and generate another differential voltage. So let me call this VSP and VSM, where S stands for sample and hold. So the sample and hold output goes here, and we want V out P minus V out M to be equal to some gain, hopefully as large as possible, times VSP minus VSM. So in other words, we are interested in amplifying the difference between VSP and VSM. Now whenever you are asked to amplify the difference between two voltages, what is the first circuit that comes to mind? The differential pair. So let us start along those lines. The tail current is denoted by 2 I naught. The two voltages VSP and VSM can always be written as the sum of a common mode component and a differential mode component and common mode component minus a differential mode component. So I am going to denote this by VCM plus VD and this by VCM minus VD, and as usual two load resistors to supply. Let us quickly review the quiescent operating point. So, to determine the quiescent operating point, we will assume that the difference between the two inputs is 0, in which case the quiescent drain potential will be is simply VDD minus I naught R the incremental voltage on the right leg of the differential pair will be plus GM R into VD. What about the left side? It's minus GM R into VD, right. Now, in order to get a larger gain, I mean clearly the incremental gain is GM times R. So, in order to increase the gain without increasing the quiescent current or the transistor size, one seems it seems tempting to go on increasing R. Unfortunately, as R keeps increasing and if the supply remained the same, the quiescent potential at the drain of the transistor, which would normally be VDD minus I naught R, would become lower and lower and eventually cause these transistors M1 and M2 to go into the triode region. The only way this can be prevented is by raising the supply, which is not practical thing to do. From our experience with circuits earlier, what do you think we should now do? So, the solution to this problem is to not use a resistor, but employ an active load instead, where the idea is to replace the load resistors with current sources, and this enables a large incremental gain without increasing the supply voltage. Is this clear? Now, the circuit is symmetric around this axis shown in green, therefore, it should be possible to use half circuit analysis to understand the operation of the circuit. So, let us try and see first how this circuit looks for common mode inputs, right. And please realize that if we are interested in high gain at all, one must make sure that all the transistors are operating in the saturation region. And so, when a purely common mode signal is applied, in other words, let us just say these two are the same potential, the first thing to do is to determine the quiescent operating point, and because of symmetry, one can split this tail current source into two identical ones, of strength I naught, and since no current flows through the leg in the middle, one can get rid of it. So, as far as the operating point calculation is concerned, all that one needs to worry about is one of these halves. So, let us try and understand what the operating point will be with the aid of this half circuit. this is VDD, this is I naught, and this is I naught, this is VCM, and we are interested in the node potential at x. So, if the tail current here I naught and the current source in the load were exactly identical, right, up to the 200 decimal place, then one can say that the amount of charge flowing into node x is exactly the same as the charge which is being removed from node x in a particular interval of time. Therefore, no net charge is flowing into node x. So, the potential of node x will stay put at its whatever value it was. Okay. So, hoping that x was initially at such a potential that the transistor M1 operated in saturation, we see that things seem to be okay. In practice, I naught in the tail and I naught in the load are built with transistors, and these are by definition independent current sources, which means that they will not be exactly identical. It is impossible to make them exactly identical. The only thing one can do is to make sure that they are only approximately the same. Now, let us assume that the two are off by a small delta, where this delta can either be positive or negative. If delta is positive, it means that the current being pumped into this node x is larger than the current that is being withdrawn from x, which means that net charge is going into node x, which in turn implies that the potential of node x will keep going up. Now, in the ideal world where the current sources are ideal, this potential will go to infinity, but in practice we know that this current source which is in the load network is being implemented by a what kind of transistor? Is being implemented by a PMOS transistor, which will cause, if the potential of node x keeps increasing, it is only a matter of time before the source drain voltage of that PMOS transistor or that combination of PMOS transistors becomes so low that the transistors enter the triode region, and thereby this current source is no longer a current source, which means that you do not get the large gain that you are looking for. Is this clear? By the same token, if delta is negative, the current being pulled out of node x is larger than the current being pushed into the node x, thereby causing the potential of x to drop. It will keep dropping. The first casualty will be the transistor M1, which will go into the triode region. The moment M1 goes into the triode region, the potential at its source will track the potential at its drain, which should not happen if M1 was in saturation, correct. In saturation, the potential at the drain and the source are isolated, right. The moment M1 goes into the triode region, the potential at the drain, namely Vx, will also reflect at the source, and eventually the tail current source will also go into the triode region, right. And since M1 has gone into the triode region and its current is reduced, the gain again will be very small. Is this clear? Okay. Now, the sole reason for this problem is that the potential of node x is being, or two current sources which are independent are controlling or attempting to control the potential of this node, right. And since the two of them are mismatched, which will happen in practice, the potential of node x either attempts to go towards infinity or ground, or to minus infinity, and will get limited to voltages which are close to VDD or ground, as the case may be. Okay. Since the problem is therefore that the potential of x is not being, we are not able to set the potential of x to a stable value, because these two current sources are independent. Okay. So, the potential in node x is being controlled by two independent current sources, and for instance, if you are in a company and you have two independent bosses who are telling you different things to do, right, obviously it is only a matter of time before you go insane, because each one of them wants you to do different things, in this particular case opposite things. One wants to push you to go up, the other one wants you to go down, right. So, that is clearly a problem. So, the only way to maintain sanity, right, or the potential of node x for that matter, is to make sure that these two people who are trying to control the potential of x talk to each other, right, so that they are saying the same thing. And the only way that can be done, if both of them are talking to each other and agreeing with each other, it means that both of them are not really independent, one of them has to be dependent on the other, right. And there is no harm in, or loss of generality in, making the tail current source independent, right. This is not necessary, but as an illustration I will just use that, right. In other words, I will assume that this tail current I naught is independent and the load current is dependent on I naught, right. So, in other words, the load current is not some random I naught, but is chosen to be exactly equal to the strength of the tail current source. And so, basically what we need is a variable current source, because it has to be dependent. So, what is the simplest variable current source you can think of which will push current down? No. What is the simplest? I mean, you need a variable current source here, and it must push current down. So, what is the simplest way of doing this? A PMOS transistor, and this is the control port, and you want to make sure that this node potential is constant, and making this node potential constant, or rather you want to make sure that the load current is exactly equal to the tail current, and instead of comparing currents, one can, as you are well aware from prior experience, you can simply monitor the potential at node x. If Vx goes up, it means that the load current is too high, which means that if this is Vg, IL is too high. So, what must be done? Must increase Vx, right. So, this is a standard negative feedback process. So, increase Vg, sorry, this is a standard negative feedback process. So, if you assume the availability of some kind of forward amplifier, in this case I have just assumed it to be an ideal op amp, if this goes up, the output must go up, and therefore, I compare Vx against a reference and kick Vg up or down depending on whether Vx attempts to go up or down, correct. So, in steady state the potential of node x will be at Vref, and Vref must be chosen to be high enough so as to keep M1 in saturation, okay, and low enough that the load transistor M3 does not get into the triode region, all right. Okay. So, recall that this is the common mode half circuit and must only apply to common mode signals. So, in other words, we want our preamp to have a common mode equivalent which looks like this, all right, and a differential mode equivalent which looks for small signals like this. I have drawn the resistor in dotted lines simply to indicate that resistance is very high and should ideally be a current source with an incremental open circuit as the equivalent impedance, okay. So, what do you suggest we do? So, in other words, this must be the common mode equivalent and this must be the differential mode equivalent. And another point that I wish to bring to your attention is that the incremental impedance looking in upwards from the drain of this transistor M1 is, if the op amp is ideal, please realize that the potential at this node which was the Vx remains at Vref regardless of whether current is pumped into the node or pulled out of the node, since the voltage at node x does not change in response to currents injected into that node, it behaves like an incremental short circuit, which means that the incremental impedance looking upwards from the drain of M1 is 0, correct. So, in other words, since this is the common mode equivalent, it implies that this feedback loop makes the common mode impedance, simply because it is appearing in the common mode equivalent circuit, the common mode impedance looking in from the drain of M1 is 0, right. So, this, let me just add that note here, ZCM is ideally 0. In practice, the gain of the amplifier will not be infinite. If you call it A, then the in practice, of course, ZCM will be 1 over A times GM of the PMOS transistor, right, and this is easy to establish. You just apply a voltage, measure the current and so on. On the other hand, let us observe what the impedance is looking in here. What is the differential mode impedance it should, I mean we want it to be the output impedance of that current source, which we ideally hope to get, I mean ideally we would like it to be infinite, but in practice we will take whatever we get, in the sense that if you maintain the transistor in saturation, its GDS is what we would like to get. Okay. Now our job is to find a circuit whose common mode equivalent looks like this and whose differential mode equivalent looks like this, right. So one thing that one can think of, I mean whenever you are given a half circuit and want to find the real or the full circuit, what do we know? The half circuit is basically is symmetric about some axis. So what I would normally do would be to copy and paste, right, about some axis of symmetry, and let us see what we arrive at. All right. Okay, so if this is VCM plus VD, this is VCM minus VD, correct. The source, please recall that in the differential mode equivalent we want the source of this transistor to be grounded. So what should we do? Connect what together? We need to connect the sources together, okay. All right. Oh, I am sorry, the polarity of this is, I made a mistake, okay. All right. Now in the differential mode equivalent, without doubt this terminal is a short circuit for balanced inputs. Now what about the common mode? So as far as the common mode equivalent circuit is concerned, we seem to be doing okay. What about the differential mode impedance at the load? The op amps are ideal, so if the op amps are ideal, we see that regardless of whether you inject a common mode current or a differential mode current, right, the two voltages at these nodes, right, let me call this x and y, the potentials at nodes x and y remain put at Vref regardless of whether you push two currents in the same direction or two currents in the opposite direction through nodes x and y, right. That is because the op amp, which is supposed to sense only the common mode potential at x, right, is sensing the total potential at x. You understand? Let us get back to this circuit. This is the common mode equivalent. This is what we want the common mode equivalent to be. And what is the op amp doing? It is sensing the potential at x and controlling the gate of the load transistor, right. So in the context of the entire circuit, it must be interpreted as the op amp is sensing the common mode voltage at node X, because after all we are talking about the common mode half circuit. We are supposed to sense the common mode potential at node X and go and tweak the gate of the load transistor, alright, so that the common mode voltage at node X is exactly equal to the reference, right. This makes sense, because this is what half circuit analysis is all about. Every impedance you measure is the common mode impedance, right. Every gain you measure is a common mode gain, every voltage you sense is a common mode voltage, every current there is a common mode current, okay. So what we are supposed to be doing is to sense the common mode potential at node X and tweak the gate potential of the PMOS transistor appropriately, so that the common mode at node X is held constant at Vref. But the mistake we have made when we have simply copied and pasted the circuit, as is common with this half circuit analysis, is that instead of this op amp is now not sensing the common mode potential at X, it is sensing the total potential at X, which is the sum of the common mode and the differential mode, alright. Does this make sense? So in other words, what we need is not this set of loads, what we need is one op amp which senses the common mode potential at node X or Y. By definition, the common mode potential at X and Y are the same, okay. So given two nodes X and Y, how will you sense, what is the meaning of their common mode potential? The common mode potential of two nodes is simply the average of their two potentials. So if you have nodes with potentials Vx and Vy, what is one very simple way of measuring their average? Yeah, one can say one way of computing their average potentials is to simply use a resistive divider, though this is not the only way one should do it. Let me call this RCM and RCM, just to remind ourselves that we are dealing with a network intended to measure the common mode value of these two potentials. Now what are we supposed to do? No, we compare this with a reference, okay. So Vref, and then do what? This must be connected to the gates, and which must be the positive terminal of the op amp? The left side of the op amp must be the, right. So what is the, so in the common mode equivalent circuit, what happens to RCM? No current flows through RCM in the common mode equivalent, which means that they can be replaced by short circuits, because the voltage drop across them is 0 only in the common mode equivalent, okay. So this now represents a circuit where the common mode equivalent is what we had put down, alright. What is the differential mode equivalent? For differential mode signals, what happens? This node potential goes up, this node potential goes down. So what happens to this potential? this node potential is grounded, this node potential is, the source coupled node is also grounded. If this voltage is 0 incrementally, what is this voltage incrementally? That must also be 0, but because that is simply a multiple of the input voltage. So, for differential mode signals, what is happening is that we have an equivalent circuit which looks like this, where the transistor M1 is grounded at the source, and in the drain what do we have? We have RCM, assuming the PMOS transistor has got infinite output impedance. Is this clear? So, if you want to get a lot of differential gain, I mean, can you comment on the size of RCM you need to choose? When you want to choose RCM to be very large, okay, and as I said, I mean, the reason why you want to choose RCM to be very large is because even though RCM does not appear in the common mode equivalent, it loads the differential mode part of the circuit, causing the differential mode gain to become small. One simple way of fixing this problem is to use buffers here, at least in principle. This is one way of making sure that the RCM resistors do not load the differential output, correct, because the currents through RCM are being supplied by those voltage controlled voltage sources. So, in general, a differential amplifier with common mode feedback will look like this. All right. So, this is a common mode detector whose job is to generate the or sense the output common mode voltage. One simple way of doing it, as we just saw, is a resistive common mode detector, which simply is a potential divider. Unfortunately, it loads the differential mode equivalent also. You compare this with some common mode reference and use some kind of amplifier, not necessarily an op amp, in order to tweak the gate potentials so as to make the output common mode reference, when the output common mode voltage exactly equal to the common mode reference that you have set. So, this is a block diagram form of a differential pair with common mode feedback. So, this network whose job is to monitor the output common mode voltage and apply corrective potentials at the gate of the load to make sure that the supply, the output common mode voltage is indeed at the desired reference, is called the common mode feedback loop. Okay, the actual feedback loop runs through like this. Is this clear? Okay. Now, there are any number of ways of implementing the common mode detector and the so called amplifier. So, you will have any number of ways of implementing a common mode feedback loop, right, but this is the basic idea. In several implementations, this VCM ref may not be an explicit one. Okay. A good case in point is the following. I think one of you had suggested this when I was discussing the common mode half circuit. Right, all of you are aware that instead of using an op amp, one could, this node potential, if this node potential is going up, we need to make this also go up. So, there is no need to use an amplifier in principle, one could actually connect these two. Okay. Now, if this is the common mode equivalent, how do you think the actual circuit will look like? Can I do this? As usual, what this is telling us is that the output common mode must be fed back to the gate, not the absolute voltage itself. So, what one must do must be to sense the common mode some way. The easiest way is to simply do this as I had indicated before and put this here, right. So, if I now call this RCM, the incremental gain is, it is simply GM times RCM. Okay. All right. So, these resistors only appear in the differential mode equivalent, all right, and this is an example where there seems to be no explicit common mode reference, right. What is the final output common mode voltage? What will it settle to? Pardon? It will simply, the final common mode voltage that will occur is VDD minus VSG of the PMOS transistor, which of course depends on VTP and square root of 2 I naught by mu p C ox W by L. Is this clear? All right. There are also other conceivable ways where you do not need to load the outputs with resistors to measure the common mode. Another way of measuring the common mode, for instance, would be to convert these voltages into currents, right, and add the two currents up, which now has got information on the output common mode voltage in current form, compare it with the reference current either explicitly or implicitly, and use that information to go and tweak the gate voltage. Is this clear? Okay. And again, the control, as we discussed before, we assumed that these two are independent and the load currents are dependent. One can reverse the situation and say the load currents are independent, and I am going to go and tweak the tail current to make sure that the common mode at the drains of the two input transistors remains fixed. Okay. So, there are any number of ways of making this work. All right. In the next class, we will figure out, now that we have made a fully differential amplifier with some gain, we need to add all the rest of the pieces of the puzzle, right, and most critically we need to interface the latch to the preamplifier in the right manner. Please recall that the preamplifier output is only relevant at the sampling instant of the latch, right. After the latch samples, the preamp can be used for other things, say auto 0, say whatever else, because the output of the preamp is not relevant at that point in time. You understand? So, we look at timing and the complete comparator slice, which is in this simple case a preamplifier followed by a latch. Okay, the next class. Okay.